you please explain that in that local relative efficiency that you were describing, you were telling that why we should always take the form n to the power alpha into that variance,
Uh,
in n to the power alpha into n to the power alpha into that risk,
right.
and why not that ln n? Can you explain that part only just once more?
Because
Oh,
we saw that if you consider log, for example, log n, right? There,
yes,
and
sir.
then there could be a problem. Let me just check if I can. Uh, so let me just check. So yeah, so let us consider this scenario. Uh, so suppose log n times delta n minus g theta goes in distribution to normal 0 v theta, right? So here your normalizing thing is different from that of the order n to power alpha, right? Now if log n delta n minus g theta goes in distribution to normal 0 v theta, then for any fixed positive integer m, log of mn delta mn minus g theta also goes over there. So
Yes, sir.
I just replace n by mn, because if n goes to infinity, mn also goes to infinity. That means log of mn delta n minus g theta goes in distribution to normal 0 theta. But log of mn is same as log of m plus log of n. So that means log of n delta n minus g theta plus log of m delta n minus g theta goes in distribution to normal 0 v theta. Right? But this is going to normal 0 v theta, so delta n minus g theta would go to 0.
Yes, sir.
Right? Now, if delta n minus g theta goes to 0, then log m into delta n minus g theta would also goes to 0, because m is a fixed quantity.
Yes, sir.
So the thing which we had considered with log of mn, and then writing log of n as log of n plus log of m, the second term goes to 0. That means this says that log of n into delta mn minus g theta also goes in distribution to normal 0 v theta, right? Because when I put a m, with m it goes to this, but with m when I put it, that becomes log of m plus this thing, but this is going to 0, right? So this is what happens. So you have this as well as this. So you have two estimators, one based on delta n, one based on, so area, it's what it says. The relative efficiency of delta relative to delta would be mn by n.
Yes, sir.
So that would create a m, so which is arbitrary, right? So that is why there is a reason why you should always look for normalizing constant of the type n to power alpha. Is that okay?
Mm-hmm. Okay, sir.
Yeah. Any other doubt?
Sir, but sir, here M is fixed.
Yeah.
So, so for any fixed M, we get to fixed efficiency. So, why is the problem?
No, no. What I am saying is whatever may be, my estimator is delta 2,
Hmm.
right? My estimator is delta 2. So what is the definition of a relativity? Suppose that delta n1 and delta n2 are two sequences of estimators, just as such that for some alpha going. So I'm saying n to power alpha, n to power alpha, this I make it
Hmm.
same. And
Okay.
then these may vary, right?
Hmm. Hmm.
I'm saying I'm considering delta only.
Oh,
My estimator is same.
oh, acha, okay.
Then here, when I make it log n, here for the same n, for the same delta, you might get mn, and in one case only one n. So that means it says the relative efficiency of same estimator relative to the other is mn, right? You see, this ensures that they are going to the at the same rate, because asymptotically for comparing two estimators, you must make sure that first they go at the same rate. Otherwise, the one which is going to zero at a faster rate is preferable, right?
Yes, sir.
Right. So here I first ensure that they go at the same rate. Once I have ensured the same rate, then I consider what their variances are, right? What are the sample sizes, corresponding sample sizes are, n prime and n. Now in this case, I have ensured log n for both. But delta
Oh,
requires n sample size here and mn sample size over here
oh,
to go to the same normal
hmm.
0 with theta, normal 0, 0 with theta.
Oh,
So what
okay,
does that
okay.
mean?
Hmm. Okay,
Relative
sir, I got
efficiency
it.
of delta relative to itself is
Hmm.
keeps on varying, right?
Yes.
Is that okay?
Okay.
Yes, any other doubt?
Sir, before the limiting distribution approach,
Right.
when you have given one example on the order of expectation and variance,
Okay. Yeah.
so there in the example, what is the objective? Because you have only derived the expectation expression for expectation and variance.
Let me just check which this problem you're talking about, normal theta one.
Yes, sir.
Yeah. So I want to see. You see, first of all, any good estimator should be consistent, right?
Yes,
Then so one thing from here, so to be consistent, one thing is if you can show that expected value goes to zero and variance goes to zero, that should be good enough, right?
yes, sir.
That means getting the orders of the movements of these estimators is important, right?
Yes, sir.
So what I'm trying to get over here is I'm trying to look at what are the orders of variances of estimated delta n1x, which is the UMVV, right?
But sir, UMBV is also unbiased estimator for theta. Then why are we proving that expectation delta and x in that expression later part? So what is the need for proving that?
Which one?
Uh, as delta n is UMBV, so it is
Is it actually-
automatic.
Yeah, so that is not necessary. Actually, here this U naught, there is some problem somewhere, right? This term should not be there.
Yes, sir. That is my question because as it is UMBV, so it is
So I'll tell you this.
automatically unbiased.
So this is in this problem. There is a some problem over here. It should be only phi of u naught minus theta plus order of 1 upon n square. Because 0
Yes.
is order of 1 square. 0 can always be written as 1 upon n square. In fact, in this case, you know exactly this is equal to this. Right? So there was no need. You are right that there is no need to write it down. This is certainly wrong. And I'll tell you why it is. So you see, the variance of delta n2 is phi square u naught minus theta t plus. So here you get the order of the variance. What should be the order of the variance? Right.
Yes, sir. That is fine.
So for example, let us look at. I'm trying to look at delta nx, which is Cn times x bar. It is not Cn times x bar. Actually, if you look at, I think one of you asked this question through.
Yes, sir. In forum,
Yes, sir.
Gauri
Yes.
has asked.
So it is not Cn times x bar. You write down this as T of x bar, where Ti is nothing but ui minus xi. Is that okay?
Oh, okay, sir. Yeah.
I define a new variable Ti as ui minus xi.
Hmm.
And T bar is nothing but u minus x bar.
Hmm.
Right?
Okay.
U minus xi, then T bar is same as u times x bar. Then this becomes delta nx becomes h of Cn T bar. Is that okay?
Hmm.
Where Ti is nothing
Okay,
but
sir. Yes. Now it's fine.
naught minus xi. Then you repeat all this. So everything you'll have to do it. You'll have to do it on Ti as u naught minus xi. And what is Ti is T1, T2, Tn are IID normal u naught minus theta I. Sorry, u naught minus theta and variance as 1. Right? So mean is u naught minus theta. And what is your h? H is phi of, actually h will not be phi of u naught minus x, h will be phi of now x only, right? Because Cn of t bar you are considering. So h of x will be phi of t. Is that okay? Is that okay or not?
Yes, sir.
You see, because I am writing down delta nx is, I define ti as u naught minus x bar, xi. Then it becomes t bar. U naught minus x bar becomes t bar. So it becomes phi of root of n upon n minus 1 t bar, which is same
Hmm.
as h of Cn t bar, where Cn is this quantity. And what is hx? Hx is phi of x. Right?
Yes.
Now you repeat it and then you will get it, and then you'll see that you not get this term. Right? So this example you'll have to modify a little bit. Is that okay?
Hmm.
Does that
Okay.
clarify the doubt?
Ah.
Yeah. Okay. Yes, any other doubt?
Sir,
Yeah.
sir, can you again explain the definition of big O 1 by n to the power alpha and small o 1 to the power n to the power alpha?
What?
Sir, the definition of big O and small o.
Hmm. So you see, big O is, so when I say something is big O, big OH, what does that mean? That means it is some function of H, which when divided by H goes to a constant. Right? For example, AH plus BH square, right? AH plus BH square. What kind of a quantity this is?
E is here exponential or
A is a constant, AH plus BH square.
AH plus BH square quadratic?
Right, just AH plus BH square.
Hmm.
So it is little OH or capital OH?
Sir, if we divide it with h to the power alpha, it will go to a constant. It is big O.
Big OH, right?
Yes, sir.
Big OH, right? Is that okay?
Yes. Yes.
That is what it means. And something I say is little OH, if you
It
divide
will
it by H,
it will goes to 0.
goes to 0. It is some function of H. So little OH or capital OH are some functions of H.
Okay, sir.
Those functions are such that in one case, little OH, if you divide it by H, it should go to 0. And in the capital OH, it is such a function that if you divide it by H, it should go to a constant.
Okay, sir.
Right? Is that okay? So for
Okay.
example, when you write down e to the power x as 1 plus x square plus so on, I write down this as ex is equal to 1 plus big O x.
Okay, sir.
Right? Is that okay?
Sir, big O H. It means we have to divide it with H.
X. X and it goes to constant.
Okay.
E to the power x when I'm writing. Is that okay?
Okay, sir.
Is any other doubt?
Sir, where you have disproved that limiting risk is not always same as asymptotic variance.
Right.
So in that example, I have some difficulty in understanding. So
Which
it is after you have defined error rate is not unique. After that part,
no, in the limiting case, asymptotic case, right? Yeah, limiting
yes,
variance and
yes.
asymptotic variances may not be the same. So what is the problem?
So in this example, what is our delta and g theta and kn?
No, what is?
Delta n and what is g theta and what is kn?
No, there is no delta n. There is a tau n or pi
But
n.
sir, in the question you have defined that we have to prove that limit n tends to infinity, expectation kn square delta n minus g theta whole square is not equal to tau square theta.
Oh,
That we need to prove. So in this example, then what is the delta n, what is kn and what is g theta?
delta n is Zn only, na?
Yes, sir.
I'm showing the distribution of Zn.
Yes, sir.
Zn goes
Uh,
to phi z.
hmm.
Right.
What is kn?
Kn is 1.
But sir, limit n tends to infinity, kn has to be infinity to define limiting risk.
Doesn't matter. You can always play around with this. You can always multiply it by this and divide it by this. So that is not that important. You see, the idea of this example is so that limit and when you see when you did probability theory, I said Zn. The idea of this is to explain that if Zn goes in distribution to Z, right? That does not necessarily mean that expected value of Zn goes to expected value of Z,
Yes, sir.
right? That is what it is.
Okay.
That is what I'm trying to show over there. Right? Now, in terms of Kn, it is exactly the same thing as saying that it is some other constant. Kn can be consumed inside this. You see, you can write down K and Zn over here. I define Zn as n times Zn, n times y, and I just multiplied by, sorry, I multiplied by 1 upon n and then take it outside. Right? So that is not that important.
Okay, sir.
The idea which is being conveyed is if Zn goes in distribution to Z, that does not mean that movements converge, right? Convergence in distribution does not imply convergence in movements, always. That is the whole purpose. And that is the reason why I'm saying that two approaches are same, different. Although in the most of the examples you see that limiting risk efficiency of two estimators turns out to be same as the asymptotic risk efficiency. But it may not be always the same. Is that okay?
Yes, sir. Sir, in the Kramer bound theorem,
Right.
there p theta is greater than equal to g dash theta whole square divided by small I theta or capital I theta. What would be that?
This is capital I theta, single observation.
Acha. Okay, sir.
Because you see, root n has come over here. When you did your usual estimation theory, it was n times I theta was coming over here. Na?
Yes, sir.
That n has been consumed over here in root n delta n minus.
So this I theta is same as small I theta.
Single observation basically, depend on how you
Oh, okay, sir. So then, in
The
the
information contained in a single observation.
okay, so in the heuristic proof,
Right.
so there in that proof, I have some difficulty in understanding that where would we use the second part, that is equation 2.
You see, heuristically, it is okay because you always know that if you apply the Kramer lower bound, any estimator which is unbiased, its variance would always be greater than or equal to n times variance would always be greater than or equal to n times g prime theta whole square by n times I theta, right? From your this thing. So that means n times variance of that will always be greater than or equal to g prime theta by I theta, right? And that is what exactly it is saying. That you have any unbiased estimator, delta n minus g theta, that means it is asymptotically unbiased, and it is going to normal 0 v theta, then I know that variance of this would always be greater than or equal to g prime theta upon n I theta, which is what exactly I have written down over here, right? So that is the heuristics approach. But of course, one has to give a detailed proof of it. So what is the problem with you?
Here you have provided that you have assumed that limit variance root and delta n minus g theta equal to v theta.
Right.
So for that assumption, we need that delta n is some function of x bar. So it is
Not
a
X bar. Delta n is any unbiased estimator.
but sir, in the remark that equality holds when yn equal to h of x bar.
Where it is? Where I have written down?
Sir, in the previous example of limiting risk not equal to asymptotic risk.
Which example you're talking about? This example?
Not example, sir.
Here, sir, here in the remark.
One in the remark that limit expectation yn squared greater than equal to expectation y squared.
Ah,
Yes,
so
sir.
the equality is attained here. Equality is attained if delta n is hx. In general, this holds. In general, limiting expected value of yn square may not be same as expected value of y square, but it will be same if your delta n is of the type h of x bar, right?
Yes, sir. So that in that proof that you have assumed that limit variance root and delta n minus g theta is v
Right.
theta.
Right.
So for that assumption, we need delta n to be some function of x bar only.
It may be for it need not be h of x bar. Even in other situations, it may hold. If it is h of x bar, certainly it will hold. But if it is not x bar, then also in some situations it may hold. It is not a necessary and sufficient condition.
Oh, okay, sir. So that proof we have to do otherwise.
Yeah, so proof basically assumes wherever asymptotic variance is same as the limiting variance, this would be the case. That is a heuristic proof I have given. Is it okay?
So, sir, when does the asymptotic variance is equal to the limiting variance?
So one sufficient condition is it should be a function of x bar, right?
Yes, sir.
Others you don't know, right?
Oh, okay, sir.
So in general, it may not be. That's what it is being said. Is that okay?
Yes, sir. So, if delta n is not some function of x bar, then also the theorem that variance theta greater than equal to g dash theta squared by I theta that hold.
That theorem still holds. But what I'm saying is proof will be much more complicated.
Oh, okay, sir. So in the heuristic argument, that is constrained on that delta n is some function of x bar.
I have given that would always be true. What I'm saying is that result all. You see what happens once you are stating a very complicated theorem, right? I had two choices. I could have gone for a proof of this, which might have taken 5 lectures, right? So I chose, let me not give a proof of this, but let me give an idea of what is happening. At least heuristically, students should get a feel. So I said that, look, this is what is happening. There is nothing very surprising over here because it is following just from your usual thing. And as I have said, limiting variance is same as asymptotic variance in most of the situations. Because most of the situations would be very nice situations. So as I keep saying, the nature is beautiful. It is only few situations where this will not hold. So since it will hold in most other situations, this proof works in most other situations. For some situations where it does not hold, of course, you'll have to tweak little bit of proof, but the cost involved is too high. You'll have to run your proof into various pages, right? And that's the reason why I skip that proof. Rather, I try to give a feel of how that proof looks like. Okay. But if you're interested in a proof, you can look at any book or any paper on asymptotic performance of estimators. This would be there. I think Lehman, it should be there. Right? Okay. Is that clear? Does that?
Yes, sir.
Okay. So what I'm saying is this is not a proof. When I say it is a heuristics, I'm saying I'm doing hand waving. Look, this would have been this. This doesn't hold in general, but if it holds, then the result holds. So I'm saying at least in this situation, I have proved the result when limiting variance is same as asymptotic variance. Is that okay? But my proof is not a very general proof. But the result is general. Result will hold in general. Is that okay?
Yes, sir.
Okay. Any other doubt?
So in the definition of asymptotic variance, tau square theta,
Yeah.
so is it asymptotic variance of delta n or kn into delta n?
Okay, and because you see, try to understand when I am doing asymptotic theory,
Hmm.
for me, two things matter. The first important thing is at what rate it is approaching to the true value of the parameter.
Hmm.
And that idea I get from Kn,
Okay.
right? So
Hmm.
Kn minus Kn times delta minus g theta, expected value of that goes to 0 whole square, or
Hmm.
in convergence in probability. So that means if I have to look at two estimators, first of all, both should converge to g theta, right, in probability.
Hmm.
And the one which converges at a faster rate should be preferred, right? For example, if for one estimator, you know that delta n times delta 1n minus g theta goes in probability to 0. For the second one, n square into delta n1 minus g theta goes to, so which one would you prefer? The one with n or with one with n square?
One with n square.
For the one with n square. So here there is no problem. I have chosen the two and I preferred one with a, whose order of convergence is faster. It is
Hmm.
ever four.
Hmm.
But now there may be more than one estimator for which the rate of convergence is say 1 upon n. So there may be two estimators n times delta 1n minus g theta goes to 0 and n times delta 2n minus g theta goes to both estimators convergence rate is same.
Hmm.
Right. Then in this case I should prefer the one for which variance is
Less.
small. So that is why I should consider variance of n times delta 1n. Is that okay?
Oh, okay.
Right.
Hmm.
Is that okay? So that is how you define asymptotic variance. Is that okay?
Yes, sir.
Limiting variance or asymptotic variance. Yes, any other doubt? We have a quiz next week, right? You are aware?
Yes,
Yes,
sir.
sir.
Yeah.
Next Wednesday. I think.
11th.
Next Wednesday. Yeah.
Sir,
So
what will be the syllabus for the quiz?
basically this asymptotic variance, right? Whatever I'll be,
Okay, okay.
this asymptotic performance of estimators. Basically assignment number 5, related problems related to assignment number 5.
Okay.
I'll do these problems on Friday and Saturday. Try to do those problems, right?
Yes. Okay, sir.
Yeah.
Yeah.
Any other doubt you have? You don't have any other doubts? Yes, anybody? You can ask anything.
Sir,
Yeah.
uh, in that minimax rule, in the graphical representation of that minimax rule, can you explain why we are taking that r delta not equal to r delta 1 line, and then um, taking the point at lowest point at which it intersects with the concave function, and in the second case where minimax is not unique, just those two cases?
Yeah. So you see, first of all, let us look at what does the minimax rule does. Minimax rule does minimizing the maximum risk, right?
Yes, sir.
Now, in this case, my theta, the geometric interpretation which I am considering, theta is only 2.
Hmm.
R delta 0, you can call it, and R delta 1. So one parameter space I am calling, one parametric point I am denoting by 0 and another by 1. So R delta 0 and R delta 1. So my risk function is basically a point only in R2, because R delta 0, comma R delta 1, right?
Yes, sir.
So any risk point, any risk function would be a point in R2, where first coordinate represents the risk at the point, parametric point 0, and the second coordinate represents the value of the risk function at point 1. So what I do is, I have a different estimators, I have a different risk. So that means I have a different estimators, I have corresponding different points in R2, right? So I consider various estimators, and these various estimators give me various points in R2. So that means if I vary estimators, I get a set of points in R2, which I call as a risk set. Risk set means it is a set of risks of estimators as you are varying risk. So the first thing which I saw was that risk set is always a convex set. Is that okay?
Yes, sir.
Okay. Now, what is a minimax estimator? Minimax estimator is the one which minimizes the maximum risk. And this maximum is over the parameter space. Right? It is maximum of R delta 0 and R delta 1. For
Yes, sir.
estimator delta, what is the maximum risk? Maximum of R delta 0 and R delta 1. So in terms of that point, xy in R2, what is the maximum risk? It is a maximum of x and y. So what I do is, once I have drawn a, so let me come so that, let me just, okay. Can you see it now?
Yes, sir. Yes, sir.
So now let us look at, this is my risk set, right? Which is a convex set. Is that okay? R delta 0 is over here. R delta 1 is over here. So different points as I vary delta gives me the value of risk which is inside this set S. What I have to minimize? the maximum of a risk. Maximum of risk is maximum of R delta 0 or R delta 1.
Yes, sir.
So first I look at all the estimators. So first I draw the line x equal to y, right? Then I look at all the estimators whose risk are on this side,
Hmm.
on the side where x is greater than or equal to y.
Okay.
Then I'm looking at this side. What is the maximum risk?
Or delta not.
R delta naught. It is x-axis only, right? So it is
Yes, sir.
x-axis. Now I look at for all the estimators over here, for which estimator x-axis is minimum.
Hmm.
X-axis is minimum over.
Hmm.
Keep on varying. I keep on varying. I see x-axis is
Uh,
minimum over here. Is that okay?
Yes, sir.
So
Hmm.
for all the estimators over here, the estimator whose risk correspond to this point has the smallest maximum risk.
Hmm.
Now I look at over here. For all the
Yes.
things over here, what is the maximum risk?
Mm, R delta 1.
R delta 1. So for all
Yes.
the estimators over here, I see for which estimator corresponds to minimum of R delta 1.
It is that point only.
That point
That
only,
int.
right?
Yes, sir.
I see whether a estimator is here or estimator is over here. Maximum risk is only minimum at this point. And that is why
Hmm.
this point corresponds to the minimax estimator. Now look at this scenario. Here your
Hmm.
risk set is only falling on one side of the line x equal to y.
Yes.
So what is the maximum risk over here?
Always delta R delta not.
R delta naught. So I look at
Yes.
estimator for which R delta naught is minimum.
Hmm.
Keep on doing it, R delta naught would be minimum only for this point. So this estimator is corresponding to the minimax estimate. Is that okay?
Yes, sir.
Now this could have been square like this.
Hmm.
Minimax estimator would be one for which R delta 0 is minimum. But here R delta 0 is same for all the estimators over here, right? Because the same line, x-axis.
Hmm.
All these estimators are minimax. Is that okay?
Hmm. Hmm.
Yeah. Does that clarify?
Yes, sir. Yes, sir.
Any other doubt?
Hmm. Sir, w- while plotting this risk set, we are telling that R delta naught and R delta 1, we are technically varying the delta.
Right.
We are taking different estimators. So means if we take a large set of estimators, accordingly our risk set may change also, right? Means if we constrict.
It will always be a convex set.
Okay.
This set will always be a convex set. And I have said, given any convex set, you can always construct a decision for problem for which the given convex set is a risk set.
Yes, sir.
So for example, these are convex set, and
Hmm.
I'm saying by the result which I stated did not prove, there will always be a decision problem for which this set would be a risk set.
Okay, sir.
Right? So in that decision problem, the minimax rule would be over here. Is that okay?
Hmm. Yes.
Yes, any other doubt anybody has?
Sir, just regarding this only, on this point only, can you move to that first example where you showed that minimax rule? Yes, sir. Yes, sir. This one.
This one?
Yes, sir. Yes, sir. So, as while during the pre-recorded lectures, you had drawn that a convex set such that it touches that x-axis and y-axis and said that to be b0 and 0c. So in this case, particularly in this case, then we don't have such points, the such extreme points that you had regarded during that lecture.
No, that lecture we were trying to see what would be a Bayes estimator, right?
Okay,
So
sir.
what does the Bayes estimator does? It minimizes the average risk,
Average risk.
right? So it will have a prior distribution,
Hmm.
let's say, which gives weight to 0 and 1. So Bayes estimator, if you give a weight to 0, weight to 1 is already determined, right?
Hmm.
So weight to 0 is P, then weight of 1 would be 1 minus P.
Yes, sir.
What would be the Bayes risk? The average risk of R delta 0 and R delta 1. 0 has a weight P, so P times R delta 0 plus 1 minus P times R delta 1.
Mm-hmm.
Right? So Bayes risk is of the type Px plus 1 minus P times Y.
Hmm.
Right?
Yes.
I look at the line Px plus 1 minus Px plus 1 minus Py would be C, right? Some constant as you vary x and y. And
Hmm.
P is fixed. So for a fixed P, first I fix P so that when my prior is fixed, I look
Mm-hmm.
at Px plus 1 minus Py is equal to C and I try to see what is the smallest possible C. Is that okay?
Hmm.
What is the smallest value of C as xy take value in S? So I consider the line Px plus 1 minus Py is equal to C. For
Mm-hmm.
fixed constant C. It will be a line over here.
Yes, sir.
I think I might have considered. Yeah. So it is a line like this.
Hmm. Yes, sir.
But this C is not of any use to me because there is no risk point for which Px plus 1 minus Py is C because it doesn't touch the risk set.
Yes.
So what I do is, this is a line which is a negative slope. I keep on moving this line and I see, and I keep on, because for all these lines, you see what I have to see? I have to see among all x and y, the smallest c. P is fixed. So that means the slope of the line is fixed, which is negative. So
Hmm.
what I do is I keep on moving this line parallelly and I see, and I keep it moving until I get a point x, y in S such that this line touches over here, because for that C would be minimum.
Yes, sir.
So when I do it, I see it touches over here. So this corresponds to the Bayes rule. Is that okay?
Okay, sir. Okay.
So, so that has nothing to do with the minimixity. That was in the context of Bayes rule. Because Bayes rule is the one which minimizes Px plus 1 minus Py in the risk set S. But Px plus 1 minus Py is equal to C. They all lines have a same slope, right? Which is minus P
Hmm.
upon 1 minus P. Slope is same, so that means you keep on moving it and see when this line touches over here. So that means that in that case, I'll be able to find x and y.
Hmm.
Okay?
Yes, sir. Yes.
Yes, any other doubt? You can have 3, 4 more minutes. Yeah? So how's your preparations for placement going? Hmm? Going well?
No, sir.
Why?
Sir, actually, they ask coding, and we, as a stat student, were not that good in coding because in IIT they came for engineers, but they also open for statistics students. So they gave coding when,
But
so we all did not
that
able
must
to
be
do.
one company, right?
Sir, but most of them took a technical test in which they asked coding.
Oh, most of them are asking for a coding.
Yes, most of them.
But you do some programming, right? First course in
Yes, sir, but actually, sir, they were asked from data structure and algorithm, which is a CSE course, I guess, six something six level course,
thing.
in which we have you have to write efficient code,
Okay.
some algorithm based coding, not like just use for loop or
Okay.
something like that.
So they didn't shortlist anybody from stats?
Sir, shortlisting, I don't know about that because that will come at the end of November.
Hmm.
So,
But that should not be very difficult. I think that they can train during the job also. Because coding, of course,
yes,
coding depends a lot on the practice, right? More you practice, more expert you become. Certainly, computer science students have an edge over there. But
Yes,
maybe some companies who deal with analytics and all that, they may not need coding, right?
yes, sir. Sir, like Goldman Sachs, they came for analytics profile, but they also ask coding. Uh,
Acha, acha. And so Goldman Sachs is, of course, everybody
yes,
yes,
a dream
everybody is
company.
targeting that only, like kind of.
don't bother about it. Life is too long to. But nowadays, I see a lot of these kids prefer smaller companies over a big companies, right? Because the general belief is that, in fact, a lot of them prefer these new startups to work with rather than going for big companies, because big companies starting maybe starting package maybe slightly better. But in terms of future prospects, many that's the understanding I get when I talk to some of the young kids. I get the impression that a lot of them uh, would prefer to go for a startup which looks promising, which they feel that has a chance of succeeding in 5 or 6 years down the line. Because in the beginning, if they get some equity from that company and that company works, they are going to make a lot of money, right?
Yeah, sir.
So that's, of course, they play a gamble, but then that also gives you a ownership to that company, because then you start working for the growth of that company. Whereas these big companies, if if they station you in India, the nature of job may not be very satisfying. Right? It may be a back-end job, and it's okay.
Work pressure will also be high, sir, in this big MNC companies.
You see, at this age, I think the work pressure doesn't matter much as long as you're enjoying the work, right?
Yes, sir. Yes.
I hope that is the case with everybody. Nobody would mind doing the work as long as it is to one's own liking and one's own satisfaction. What hurts is that you do all the job for somebody sitting in Hong Kong. He has to do presentation, and then you prepare slides for him and do some basic data analysis, and then he gets all the credit. You're not seen anywhere in the picture, right? That sometimes could be, of course, but if you need a money, then that's okay. In the beginning, it's a good compromise. You make some good money and then decide what you want to do. 2 years down the line. There's nothing wrong. But then you can slowly move to other, you gain experience, and then you can move to other. But I think it's better to have a plan in mind that what you want to do 5 years, 6 years down the line. Because you see, everything has a limit. Money also has its own limitations. After a while, it will be just lying in your bank, and then you don't know what to do. Your lifespan is finite. So yeah, so these are difficult calls, but then finally, I think you have to.
Yes.
People are much smarter than we were. Actually lucky that we didn't have much choice, so we didn't have to really break our head after money. So whatever money we were getting, we were very happy with it. And not there were not many options that okay, you go and do it. So that way, I always say that our generation was much more luckier than the one which I see. There's a lot of options, but then a lot of confusion. A lot of options come with a lot of confusion. That's okay, but that's how you have to. That's also a part of life. to manage such complexities. And I'm sure that you will be able to do it in a optimal manner. Okay, any other doubts? Otherwise, we can disperse. We'll again have a discussion hour tomorrow, but tomorrow discussion hour will be in the morning.
Hmm.
Try to do these problems. If you want to discuss some problem tomorrow, also I don't mind discussing some problems, but I would prefer that if you can clear your doubts first, that would be more appropriate. But if you want to come up with some problem from the assignment, that also would be this. Fortunately, this time I have been able to write down solutions for all the problems. So it took a lot of time, but then I prepared solutions. So after Sunday's tutorial, I can upload them. But still, I would encourage you to do these problems of your own. And in case of any difficulties, anyway, we'll discuss it on Friday and Saturday. Tomorrow also, apart from discussing these regular doubts, we can discuss the problems. Is that okay?
Okay, sir.
Yes, sir.
Okay,
Yes, sir.
and see you tomorrow.
Okay, sir.